Alright, so this is Physics 1C for April 29th. Today we're talking about Ampere's law. So this is going to be kind of, I guess, the third of the Maxwell equations. I know it's called Ampere's law, but Gauss's law and, well, we have two Gauss's laws. There's the Gauss's law for magnetism and the Gauss's law for electricity. I guess we didn't talk about Gauss's law for magnetism, did we? Maybe we should talk about this today. Anyway, so we kind of did, but we didn't explicitly say it.
Mm-hmm.
All right, so let's do Ampere's law, and then we're going to do a problem with the solenoid down here, and that will be all we'll do today. I don't know how long this will all take. Okay, so Ampere's law is kind of, in a way, motivated by the idea of electric potential or voltage. So what we're going to do is we're going to start off with a wire that has current in it. It's actually kind of shown in this picture right here. So let's say we have a wire and it carries a current I, and that current is coming out of the pages U. What we want to do is basically do a line integral around this. So we draw a circle, and we say that our circle has a radius that's r. And kind of what we want to do is say, well, we know from what we did yesterday that the magnetic field that's produced around this wire is going to be circular in nature. So this is the direction of the magnetic field. It goes in a circle around like this. And so what we'd like to do is to kind of evaluate a line integral where we come here and we take little line elements, dl, at every point on the circle. And these line elements are kind of guaranteed to point parallel to the magnetic field if we made our path a circle. And we want to just evaluate what we get if we, if we perform a line integral around here. And why would we do that? Well, just as a motivation, remember that the definition of electric potential, delta V, is negative integral E dot dl. And so what we're going to do is the integral of B dot dl. Right, so if E dot dl gives us voltage, which is a pretty useful concept, right? It's kind of the way we measure energy for batteries and other types of power sources. Then what do we get if we do the same thing for the magnetic field? And in this case, what we're going to do is we're going to do a closed line integral. So we're going to go around a complete path here. Now, before we even do this, I kind of want to ask a question about voltage real quick and see if you remember, or you can figure this out. What would happen if I did a line integral of E dot dl with this left equation here? And to give you an example of what that might mean, let's say that I give you a circuit, and the circuit has a positive here and a negative here. And within the circuit, all we have is just a resistor to keep it simple. Okay, so here's our resistor R. And here's our battery with an EMF. Suppose that I came to some point right here, and I did a line integral around this one. And I came back to the exact same location right here. What would I get? If you can't figure out what you would get over here, you can look at the left-hand side. What would delta V be between this point and itself?
Just be zero.
It'd be zero, right? So we know that for electrical circuits, that when we perform this operation, we get zero, right?
Mm-hmm.
So the question is, if we do the same thing for a magnetic field, are we also going to get zero? Or are we going to get something else? So let's figure it out. Okay. So integral B dot dl means we take the value of the magnetic field and we dot product it with dl. Now, since the dl and the magnetic field point in the same direction, then that means that this can basically just become bdl. The next thing we can do is we can say we've already calculated what the size of the magnetic field is. We know in this case that the size of the magnetic field is equal to, this is what we learned last time, the magnetic permeability multiplied by the current, and then you divide by 2 pi times the radius. This is what we derived last time using the Biot-Savart law. So if we plug that into our equation right here, we're going to get that, which is now going to become, so the radius is a constant along this path because we took a circular path. It's not changing. And the current is usually a constant. It's certainly not going to vary from point to point on the path right here because the path is basically symmetrical. You know, I can rotate the path and it's not going to change it anyway. So I is a constant, mu naught's a constant. Everything in the magnetic field definition here is a constant. So we can pull all of that out. This should probably remind you of the kind of Gauss's law problems we did, right? Where you pull the electric field out of the equation. And then what we're left with is just this line integral of dl, which, what is this equal to?
2 pi r.
Right. So now what we end up with, so this is times 2 pi r. We basically just get mu naught times I. So the result is this. We started with doing the line integral of b dot dl around a closed path. And what we end up getting is mu naught times I. This is Ampere's law. And we got here kind of similar to how we arrived at Gauss's law. I say derived, we didn't really derive anything. When we derived Gauss's law, this is exactly what we did. We just said, what do you get when you do the integral of E dot dA? And the answer was you got Q naught, or you got Q divided by epsilon naught, where Q is the charge enclosed. So it turns out in this case that the answer that we get is also going to only depend upon the amount of current that's actually enclosed within the loop. Okay. Now specifically what this is the current enclosed represents the current that passes through any plane plane's the wrong word, because I think when I say plane, you're going to think something that is not what I mean. So I'll use the word surface. Through any surface bounded by the path. So the path is going to be the path of the integral, right? So I think often the way this is written in mathematics, maybe I'm wrong, is you put a little c down here. Is that right? To represent the...
Yeah.
Okay. The C doesn't mean closed. It's like circle or something. What is it? What does the C stand for?
A curve.
A curve. Okay, so that's to be compared with when we do the surface integral. You put an S here. And when you do a volume integral, you put a V here, right?
Mm-hmm.
So C is for curve. Okay, I didn't actually know what that was. Okay, so whatever that curve you're using for your path is, the only current that we're going to include is the current that passes through a surface bounded by that path. So for example, what is a surface that's bounded by this path?
Circle?
It's a circle.
Yeah. Or I mean, when we say circle, we really just mean the path itself, right? So it's
Yeah.
it's really this, right? It's like a disk. That is the surface, right?
Mm-hmm.
Okay. So, just as a way of kind of like broadening out what this equation says, suppose that I take several different values of currents. So, I take a current here and I tell you that it's 5 amps, and the dot represents that it's going out of the board. I put a current here and I tell you it's 7 amps. I put a current right here and I tell you it's like 9 amps, and maybe one right here and I tell you it's 3 amps. Okay? With the x's meaning they're going into the page and the dots meaning they're coming out of the page, right? And now I surround these with different surfaces. So I put one surface here, we'll call that surface 1. Put another surface right here, call that surface 2. And one more. Just put one that surrounds all of them. We'll call that surface 3. So for each one of these, suppose that we perform a line integral, or a line integral around the path, and I'm going to make all of them clockwise. I don't have to do this, but it actually matters. It matters what direction we choose. So those are our path integrals that we want to do around these objects. We're not going to worry about actually calculating this. What we'd like to know is, what is the value of the integral of b dot dl along these paths? And the cool thing is we don't have to actually do any integrals to do this, because we know that integral b dot dl is just equal to mu naught times I enclosed. So I'll do surface 1, and I'll have you all do surface 2 and surface 3. So the way you do this is the current enclosed can either be positive or negative. If it's going into the page, it's going to be negative, and if it's coming out of the page, it's going to be positive. Now that's assuming that we've made our paths to be counterclockwise. I'll talk about that in a second. But for surface 1, okay, the answer is going to be 5 minus 3. And it's multiplied by mu naught, actually. Sorry. So it's going to be mu naught times 2 amps. Does that make sense?
Mm-hmm.
Yep.
Pretty easy, actually. So what about surface 2?
Negative mu naught.
Okay, so surface 2 has 9 coming out and 7 and 3 going in. So it's going to be 9 minus 7 minus 3 amps times mu naught. So it's going to be 1 amp times mu naught. Can you see how this is really similar to Gauss's law? Where Gauss's law, you just add up all the charges inside of your surface.
Wouldn't it be -1?
Yeah.
Oh, it's -1, yeah, thank you. But anyway, you guys agree. It's like really similar to Gauss's law, right? You just add up whatever's in there.
Mm-hmm.
Okay.
Yeah.
So what is the value for surface 3 then?
Or mu.
4 amps
Mm-hmm.
times mu naught. Now let me say something about the direction of the path because it matters. Oh, it actually says it right here, so I don't want to waste time by drawing it. Let's look at this picture right here now. Okay, so these are 3 integration paths for the line integral of B in the vicinity of a long straight conductor carrying a current I out of the plane of the page. The conductor is seen end on. So there's the conductor and there's the path. This is basically the same picture that I drew over here. So magnetic field points tangent to the path. The DLs are also tangent to the path. And the value of this integral is positive mu naught I. Now, a relevant question would be, what happens when we reverse the direction of the integral? So if we go around this integral in a clockwise path, as opposed to a counterclockwise path, you see that this is clockwise, this is counterclockwise. Now B and DL are opposite to each other. So the answer that we're going to get is negative. Okay, so even though it's the same path, they're both circles, the direction we go around the path matters. So I think usually it kind of makes sense to make B and DL in the same direction. But
And that's because of the cosine of the angle between them,
yeah,
right?
Yeah, exactly. Yep. So for basically all of these answers right here, had we changed the path to go the other way, then it would have made this -2 and +1 and -4. Does that make sense? Now, go ahead.
I'm gonna. This doesn't look like it's conservative.
Right, it's not, and that's the whole point. That's why I asked this question earlier. So it's interesting, right? If we tie this back to what we learned about electricity, that when we perform the same operation, so they're both fields, right? Oh, I'm so sorry. These should have vector symbols above them. I apologize. If we do the same operation with an electric field, you basically always get 0, because the electric field is conservative in general. Now, we're going to learn in a couple chapters that there do exist non-conservative electric fields. But when you have a conservative field, this is always true. This is a mathematical statement about conservative fields, right? Is that right, Cam?
Yeah.
Like all conservative fields, this is true. And what's a conservative field? Well, a conservative field is one for which the work done is independent of the path. So in a way, this is kind of a definition of a conservative field. Another example of what's another example of a conservative field in physics?
Gravity.
Gravity is a conservative field, right? And a way of saying that is that suppose that I want to take an object, I want to lift it from this location to this location up here. All that really matters is, it doesn't matter what path you take to get there. So if I'm going between these two locations, then I can either go in a straight line, I can go to the right and then up, or I can go way up and then come back down. It doesn't matter. The work done by gravity is the same in every case. The change in potential energy is the same in every case. The fact that you can write down a potential function is only true for conservative fields. Okay, so I think in physics up till now, we have exactly three vector fields, right? We have gravity, magnetism, electricity, right? And of those three, two of them are conservative. The electric field and the gravitational field are conservative, but this right here proves, I don't know if proves is the right word, but shows that the magnetic field is not a conservative field. So let me ask this question. If the magnetic field is not conservative, is it possible to write down like a potential energy for the magnetic field?
No.
I would say no.
No.
Yeah.
Right.
Well,
Right. Okay. So there's not going to be like, there's not going to be anything like that. Okay. So I guess we should talk about this path right here, this last path. So if I choose an integration path that does not enclose the conductor, then you get B dot dl equal to 0 because the current has to be enclosed by the path. And this picture right here kind of shows that. I don't know if this picture is really super clear, but here what we have is a current carrying wire here. Let me just blow this up a little bit so we can really look at it. So here we have a wire I, and our path now goes from A to B to C to D, and then back to A again. Now from D to A, the path goes this way, but the magnetic field is up. And why is the magnetic field up? Because it's a current carrying wire like this, so the magnetic field's going to make these circular lines like this. Same thing from B to C. When we go along a path like this, you do B dot dl, then you're going to get 0. But what about these other two paths? So let's look at A to D. So if we do the integral along the path from A to D, we have a B dot dl, and this ends up being equal to, okay, what's the name of the radius now? The radius for A to D, oh, not A to B, sorry, it's A to B. A to B. So we're going from here to here, and the radius there is R1, so mu naught I over 2 pi R1 is B, and then we'd have to multiply this by the integral of dl, which is going to be 2 pi R1. So we end up getting mu naught times I, and it's positive. If we then do the integral from C to D down here, and we do B dot dl, you're going to get the same thing, but you're going to get a negative sign, because now when we do B dot dl, it's just going to become negative B dl. And that's going to end up being negative mu naught I when you actually multiply it out. So when you add them together, you get 0 around the whole path. And that happens because, well, you can see why it happens. In one direction, you get a positive contribution. The other direction, you get a negative contribution, and they cancel out. Okay. So, again, it is only currents that pass through the surface bounded by the path. Now, one thing that I want to emphasize, I should slow down for a second. Does anyone have any questions? All right, so here's the thing about this that's actually really, really interesting. It turns out that It's any surface bounded by the path, right? Any surface bounded by the path. So what does that mean? So I asked you what the surface bounded by the circle was, and you all said a circle. But I think we all agreed that it's really like a disk, right?
Yeah.
Okay.
Mm-hmm.
Okay. So what could that possibly mean? Any surface. What's another surface? I mean, the disk is the most obvious surface, right? You just,
That's something like a
Like an ellipsoid or something. That...
an ellipsoid?
parallelogram or something.
A parallelogram?
Or-
Wait.
Oh, like a flat surface?
No, look.
What about?
It's a circular path, okay? We're not going to use a parallelogram for a circular
Oh, it
path.
only could be a circular path.
Well, no, I mean, it could be a path shaped like this, or it could be a path shaped like a parallelogram. I'm asking, for this path, for a circle,
Mm.
can anyone name another surface other than a surface that's just a disk that's bounded by this path? Does that question make sense?
Like a half
Oh,
sphere?
okay.
Half sphere, like a hemisphere, right?
Yeah.
So what you're saying is basically, let's draw it like three-dimensionally. So if this is my path, obviously one of the surfaces is this right here, right? Maybe we call that S1, surface 1. But another one would be like this.
Could we also do a cylinder?
Yeah, kind of. It has to be open on one end, like a cup. So I can't draw this super well, but does this, like a net, this is like a net, right? Does that make sense?
Mhm.
Think of a net, but then kind of fill in all the holes of the net. Maybe we'll call that surface 2. A cylinder would be another option. Here, let me erase the lines for surface 1, because I want to draw the cylinder up. Another possibility could be, yeah, we could draw a cylinder. I don't know how much a cylinder is a surface. It's like two surfaces, right? But it's kind of okay, I guess. I guess if we say that the edges here are rounded, it's fine, right? As long as it's not like a sharp edge, I think it's okay. You need to have, I think it has to be a smooth surface. I probably should have said that. Okay, that would also be another surface, right? Now, if we do something like a cylinder, it's open on the bottom, right? Like, let's just use a cup as an example. Oh my god. Why can't I draw? Yeah. Okay, so that would be another example. So if I had a surface, if I had a path that was like this, then this other piece right here, the cup, would be like a surface that's enclosed by that path, or that's bounded by that path. What did I say? Yeah, bounded by the path, yeah. Okay, does that make sense?
Yeah.
So really, you can take this, the way I think about it is, take the most simple surface that's bounded by your path, which is going to be a plane. Because any path you draw, is this true? Most paths you draw are going to be in 2 dimensions. So take the simplest path, which in this case would be like just a disk, and then deform the disk. So the way I think about it is think about it like a trampoline. So if I'm standing on a trampoline, the trampoline will kind of depress, and it will change the shape of that disk. But the trampoline is still bounded by the ring that holds it, which is the path. Okay, so that's going to be relevant. Okay, not in this chapter, but this piece right here, this phrase, is the thing that Maxwell focused on to basically prove that light is an electromagnetic wave. Like, this piece right here is extremely important. The fact that it's any surface and not just the simple surface that you can think of, okay? And the effect of that is going to be that Ampere's law is not complete. This is not the full story of what you get when you integrate B.dl, because there's actually going to be another term here. And the other term is going to be related to electric flux. And what we're going to find is that not only do you get a value for this from a current, but the same thing will occur if you have a changing electric flux in the region. So that's something we're going to prove. It's going to be one of the last things we prove in this class. That's going to basically tie everything together. That's going to tie electricity to magnetism to light. And it all comes from this phrase right here. So Just kind of like letting you know that that's something that's going to come up later on. Okay. Well, it's a long problem. So now we're going to use Ampere's law for what it's really intended for. It's not really intended for just calculating this value. It's actually used for finding magnetic fields. So it's very similar to Gauss's law in that sense, right? Gauss's law is the integral of E dot dA is equal to Q over epsilon naught, but we used it to find electric fields, right? And we're going to use Ampere's law to find magnetic fields. Okay. And the first example that Ampere's law is very useful for is a solenoid. Okay. Now this word solenoid, okay, it literally just means a coil of wire, a very specific type of coil of wire. But a solenoid, solenoid is basically a coil of wire. Usually, it doesn't have to be, but usually wrapped around a cylinder so that it takes on the form of a cylinder. So, where have you heard the word solenoid before?
One pole magnet.
A one-pole magnet? Or just have you
A monopole.
some kind of a magnet? Where else have you all heard of solenoids? Does anyone here work on cars? No one? Anyone here like
I
just...
think I've heard it when cars are mentioned.
Okay. So there's a solenoid that is something that sometimes has to be replaced. I think it's related to the starter in your car. Anyway, this is all that it is. You take a cylinder. Okay. And around your cylinder you wrap wires. Okay. So I'm gonna wrap the wires like this. So they're gonna go kind of back up this way. You can't see it, but then they'll come back out the top right here, and then we'll just keep winding it like this. So it goes this way, back up this way, and then comes back here, and then it goes back up this way and comes back here. Okay, so it's basically you're just wrapping wires. It's one wire, not multiple wires. You're wrapping multiple wires. Maybe I can make it cross so it's clear that, I don't know if that makes it more clear that we're wrapping lots of wires around here. But this is what a solenoid is. It's just a bunch of wires that have been wrapped, well, one wire that's been continuously wrapped around something like this. And eventually the wire will come out like this, okay? So what we'll do is we'll say that our current is flowing in on this side and then out on this side here. And let's see if that's consistent with their picture. Nope. Let's be consistent with the picture. Let's say the current flows. Yeah, I think this is consistent with the picture. Let's say the current flows in on this side. Current goes this way. So it goes in this way, and then it just basically keeps going up. Okay, so at every piece of our thing right here, the current's flowing up, so it's flowing up here, and then the current flows basically out that way. That's a solenoid. Okay, it's basically like a lot of loops of wire that have been kind of like spread out over over the cylinder. Okay, that is what a solenoid is. Okay, so don't let it confuse you. It's quite literally just a bunch of wire wrapped around a cylinder. Okay. And if there was a phrase that meant a bunch of wire wrapped around a cylinder, I'm sure that's the word we would have used, but we just have the word solenoid. Okay, so let's look at the problem. It says, a solenoid consists of a helical winding of wire on a cylinder, usually circular in cross-section. Why wouldn't it be circular? I guess it doesn't have to be circular. It could just be like a rectangular prism technically, and this would still work. It would do the same thing. I never thought about that, but that is true. There could be thousands of closely spaced turns, often in several layers. So what that means is that you don't have to wrap these like just 1, 2, 3 like individual wires like this. You could wrap it over and over and over and over again. And the solenoids that we have at the school, that's what they're like. They'll have something like thousands of turns per meter or something like that because the wires are just wrapped and wrapped and wrapped and wrapped and wrapped. You just keep wrapping wire because we're going to find out that's how you make the magnetic field really big. Okay. For simplicity, Figure 28.22 shows a solenoid with only a few turns. So here's... Oh, I guess I didn't copy this picture. Because this isn't the same. This is the sketch for the problem. All turns carry the same current I, and the total B field at every point is the vector sum of the fields caused by the individual turns. The figure shows the field lines in the X, Y, and X... You know what? This is bothering me. I'm going to pull up the picture from the book. I didn't realize that I didn't include it, because now that they're referencing, I want to make sure you understand what they're talking about. It's just going to be a picture. It's going to show magnetic field lines, though, which is kind of nice. So we're here. There's Ampere's law. We're on applications of Ampere's law. That one. See, this picture is even better, really, but that's our picture right there. Oops. And the scrolling is real. Oh no, I went too far. Oops. Back to this one. Come on. Go. Click. This one. There we go. Magnetic field lines produced by the current in a solenoid. So here is kind of like a quarter turn. So our solenoid is basically wrapping like this. And those are the magnetic field lines that it produces like that. It's basically really similar to the magnetic field of a dipole bar magnet, because that's ultimately what a solenoid is going to do. It is going to create a very uniform magnetic field on the inside. Okay. Notice that, remember that the strength of the field is related to the density of the field lines, right? So the closer together that the field lines are, that's the place where the field is the biggest. So can you tell that in this region right here, inside the solenoid, is the place where the field lines are closest together? And then on the outside out here, the field lines are much farther apart. So the field inside the solenoid is what we're going to focus on. Okay, and we're going to assume the field outside is very weak. Okay, so here's our solenoid. Okay, so the figure shows the lines in the X, Y, and XZ planes. We draw field lines that are uniformly spaced at the center. Exact calculations show that for long, closely wound solenoids, half of these field lines emerge from the ends, half leak out through the windings, as the figure suggests. If the solenoid is long in comparison with its cross-sectional diameter, and the coils are tightly wound, the field inside the solenoid near its midpoint is very nearly uniform over the cross-section and parallel to the axis. The external field near the midpoint is very small. That's basically what I was saying, like the field is really big in the middle on the inside. We want to use Ampere's law to find the field at or near the center of such a solenoid if it has N turns per unit length and carries a current I. Okay. Now, what we're going to derive here is going to be a really useful relationship. It's going to show up in a lot of your homework problems. You're going to be given a solenoid, and you're going to want to know what the magnetic field of the solenoid is. We're also going to be using solenoids for derivations that we do in the future. So this is a really important example. I don't know if it's super important that you understand the derivation, but the result is really important, okay? And just like we always do in physics, we like to derive anything that we can. If we can't derive something, like last time we were talking about the bios of our law, can't really derive that in this class, so we didn't. But when we can, we'd like to. So we have Ampere's law. And again, just to write it down again, Ampere's law stated that the integral of B dot dl was equal to mu naught multiplied by the current that was enclosed by the path that we chose. Okay. So what we have here is a sketch for our solenoid. And it's drawn so that we're only looking at like a cross-section of the solenoid. So basically what we've done is we've taken a piece of our solenoid like this right here, and we've chopped it straight down the center so that we're looking at kind of the inside of the solenoid. And the effect of that is that the currents on the bottom down here, so this is like each one of these little dots represents a single winding. And I'll just draw a line on here to represent what's going on. The idea is that the current kind of flows out from here and then it curves up into this one, and then it goes into the page, and then it comes back down from behind, comes back out here, and then it curves and goes in there. And then it goes back, comes out this side, and then it curves down in there. So these are our coils now, basically. Right? I don't know how good I'm doing this, but does this make sense? How this is the same thing as this thing right here?
Yeah.
Mm-hmm.
Yep.
Okay, cool. All right, so once we're convinced that this is a solenoid, now what we want to do is say, let's assume that the magnetic field on the inside is pretty uniform. Again, we're looking at the center, so we're really only looking at this piece right here in the middle, the place where the magnetic field should be very uniform. So we're going to assume that our magnetic field lines are straight, because that helps us to make the calculation really simple. And we're also going to make the assumption that the magnetic field on the outside is approximately 0. It's not true. It will have some magnetic field outside, but if I could show you a demo, it's very easy to prove that the magnetic field on the outside is very negligible relative to the magnetic field on the inside. Because you can use something that's called a magnetometer, which is basically just a little magnet that is able to kind of rotate in 3 dimensions. It's just a magnet on some swivels, basically. And when you put the magnet near the inside, it is very strongly it lines up with the magnetic field, almost like a compass. But if you put the magnet out here, it's basically no effect. So it's really easy to show that, okay, maybe the magnetic field's not exactly 0 out here, but it's basically 0, I mean, all that matters in physics, all that matters in science is what you can measure. And if you have no way of really measuring how big the magnetic field is, then you might as well just call it 0, right? Okay. Plus, it makes this calculation super simple. So here's our integration path. We're going to go from A to B. And then the way that they've drawn this, actually, their idea is these little jagged lines right here, they look kind of like resistors. They just mean that points C and D are really far away from the magnet, okay? But from the solenoid, because you're free to do that, right? We can choose whatever integration path we want. And so if we make our integration path so that, we're integrating from here, and then we go really far away, and then we come back down, then if that's our solenoid right there, and the magnetic field is inside of here, I think it's pretty reasonable to say that if you get 100 miles away from your solenoid, let's say this is 100 miles, because we can make it as big as we want, that the magnetic field is definitely going to be 0 over there, for the solenoid at least. You may have some magnetic field for the Earth or something, but that's what those little jagged lines there represent. It means that this distance is not commensurate with the picture. It's much bigger than this. Okay, so let us do our calculation now. So we can see the magnetic field lines are pointing to the left. Let's go A, B, C, D. Let's go like that. Okay, so let's do the integral along AB of B dot dl. And we want to figure out what that's equal to. So B points to the left, and it is in the same direction as dl. So dl would be this way, which means we can pull the B is going to be uniform too, so we can pull it out. We're basically just going to be doing the integral of dl, which is going to be equal to B times however long this is. So it doesn't actually say, oh yeah, L. It's L, right? So it's going to be B times L. Okay, what about the other paths? What about the path from B to C? Now, from B to C, our dl points this way, right? But our magnetic field goes to the left. So what's B dot dl going to be equal to then?
0.
0.
Yep. And the same thing can be said for the path from D to A, right?
True.
So those are both 0. And then finally from C to D, this is also going to be 0, right? Because now the magnetic field is 0. So if this is 0, the whole thing has to be 0. So that means that when we evaluate our entire Ampere's law here, the integral of B dot dl around now our closed path. So I put the circle here. These were all just A, B, B. So I didn't put circles on these because it wasn't a closed path. But I put the circle on there. It means we're going around a closed path. We know this is equal to mu naught times I enclosed. So we're going to have to calculate what I enclosed is now. But we know the left-hand side of our equation is just B times L. My God, it's so simple, right? Just like with Gauss's law, you quite often never actually end up doing the integral with these kind of things, which is really nice. So this is equal to mu naught times I enclosed. So the question is, what is this equal to now? So let's figure that out. Okay, so every one of these little x's right here represents a current, okay? And in this case, that current is flowing into the screen, right?
Mm-hmm.
Now, if I want to count up how much current passes through my surface, remember that any current that passes through my surface counted, right? Like if we go back to what we did here, if I have 3 different currents, then I add up those currents. So can you tell me how much current... Oh, and we're saying the current flowing through the winding is I, by the way. How much current... So basically, this would be 1I, right? So how much total current do we have here?
Ni.
NIL.
Yeah, so in this case, how many is it, though? 1, 2, 3, 4, 5, 6, 7, 8, right? So we're going to write 8 times I. And yeah, it's Ni, right? But given a length that we're calling L, which is it's a fixed length, you know, there's exactly 8, right? So our result now, because we're basically done, is basically that in this case, the magnetic field is going to be equal to mu naught times 8 divided by L times I, right? It's a really simple result. Of course, we can do something exactly as you all said, where we could say, well, what if it was 10, or what if it was 11? What if we just made our path bigger? Would we get a different answer? Well, no, because L depends on the number of turns, right? Had we doubled L, right, if we go to 2L, how many turns would we have enclosed?
16.
16, so 2 times 8, right? So that number of 8 over L must actually be some kind of a constant, right? And it is. What we do is we say, let little n be equal to the number of turns divided by length. So it's basically the number of turns per unit length. Okay, so this is number of turns per unit length. Okay. Then our equation can just be B is equal to mu naught capital N divided by L times I, or mu naught, I like the second one. Oops. Come on. Or mu naught times little n times I. And that's the magnetic field of a solenoid. And this result, like I said, is really useful. There we go. Anyone have any questions?
What are some applications of solenoids? I know you said something about like a car starter.
So this is something where I might have to go to the interwebs to figure out exactly how it works, because I don't know. I just know that often, like, when you have a problem with your like starter, you have to replace the solenoid. You know, I remember they got my car worked on one time. They're like, "Oh, we just had to replace the solenoid." I don't know. I think that it's used to spark the engine to give it a start. So a starter solenoid is an electromagnet which is actuated to engage the starter motor of an internal combustion engine. It's normally attached directly to the starter motor, which it controls. All modern cars also use a starter solenoid to move the starter pinion into engagement. Maybe we get some pictures. So it's related to the ignition switch. I have to read more about this. Ooh. So this is the solenoid. Oh boy, this is way beyond me. I do not know. Like, looking at this does not. I don't know what's going on here. But I can say there are even simpler applications than that that we can talk about. So that was just one that I thought of. So a solenoid is basically an electromagnet, right? That's what it is. Because what this tells us is that if I take an object like this and I wrap coils around it, I basically have produced a dipole-type magnetic field, right? So anything that has an electromagnet in it is probably using something like a solenoid. Now, there's other ways that you can do this. You could take this same object right here and you can wrap it in a tube to make a toroidal solenoid, which is like a donut-shaped solenoid. That's another type of magnetic field that you can produce. And if you do that, then you get a circular magnetic field, I believe. It's confined in between it. So that would be like, take this object and wrap it into a donut. And then on the donut, now wrap turns. I can't remember if you all have a problem about this or not in your homework. I think you do, actually. I don't know if it's a homework problem or if I gave it as an exam problem one time. I can't remember. But basically, it looks something like this. I don't want to keep drawing too many of these, but you wrap your wires like this around it, right? So this would be a toroidal solenoid, and this object produces a magnetic field on the inside like this. So there's your magnetic field. This would produce your normal kind of north-south magnetic field like this. Let's see, it's wrapping. So if you want to figure out the direction of the field, you just need to wrap your fingers in the direction of the current. Current's going that way, yeah. So now the magnetic field's going to be going this way. Now, there's another application of this, which is going to show up in the next chapter, which is, and I guess I'll just preview it right now by saying, what if you put something like this into an electrical circuit? Okay? So, let's say I have a circuit, and I've got an EMF down here, and I attach it to a switch, called the switch S. And now, in my circuit, I'm going to have all the normal stuff that we can put in a circuit. So what are the passive elements of circuits we've learned about so far? We've learned about resistors, right? We've learned about capacitors. And we've looked at circuits that have resistors and capacitors inside of them, right? But what if I stick a solenoid in here? It's not going to break the circuit connection, right? Because it's a continuous loop of wire. And what would happen if I throw the switch here? Well, current would start... If I throw the switch, charges are going to start building up on here, right? Current's going to start flowing through the system. So current's also going to be flowing through this guy. And a magnetic field's going to be produced right here, right? Sure. So, think about what happens with the capacitor. What happens inside of the capacitor? Well, you produce an electric field, right? And we figured out that inside of this electric field, you could store energy. So it turns out that if you put a solenoid into a circuit, you can not only store energy in the form of electricity, or sorry, in the form of the electric field, but you can also store energy in the magnetic field. And what we'll learn is that what the solenoid does is it kind of resists your attempts to turn the current on and off. And as a result, it's going to make it so that the current does not instantly flow through the circuit. It's going to make the current kind of sluggish. It's going to make the current take time to reach its maximum value. Once the solenoid has all the current flowing through it, it's going to have this big magnetic field. And when you try to turn the current off, that big magnetic field carries energy, and it's going to deliver power back to the circuit, acting like a source. So I've just given a summary of everything that we're going to talk about for the next 2 weeks. So if that's a lot of stuff to take in, I understand. But that's another one of the applications, is you can put this thing into a circuit, and it will act as kind of a reservoir for energy. And will make the circuit kind of slow to respond to changes in current. It'll smooth changes in current out, effectively, which can be really valuable. And it turns out that a circuit like the one I've described right here is basically how a radio works. It's basically how a radio works. That's pretty much what I've just drawn here is a radio. So.
Oh, okay.
So
So when it's fully charged, then there will be no more magnetic field because there will be no current flowing.
The capacitor? Right.
Yeah, okay.
Right. Exactly. But so that's another example of an application that I know about as a physicist or whatever. But I think the reality is that if you were to open up almost any type of electronic device you have, open up a radio or your computer or an amplifier or a subwoofer or a speaker, whatever, pick up, or even in your car, open up any type of electrical system, you're going to find little coils of wire all over the place. Just all over the place, you're going to find little coils of wire. And, you know, all this stuff is kind of connected to that. So we'll learn more about how these things work. But for now, we now know how to produce magnetic fields. That's what we've learned in this chapter. We learned that you can produce a magnetic field from a wire. That's the mu naught I over 2 pi r. A magnetic field from a loop. That was like the mu naught I over 2 r, I think. And now a magnetic field with a series of loops, which is called the solenoid. So, yeah, we now know how to produce magnetic fields. We also know how to control them because we have an equation that relates the magnetic field to the current. And we had already learned in the past how to control currents, right? You get a voltage source, you get a certain amount of resistance within your circuit, you can obviously control the current because of Ohm's law, right? By changing the resistance in your circuit, you can control how much current there is. So as long as you can control current, which is very easy to do, then now you can also control magnetic fields. And, you know, tune them to precisely the value that you might need for a certain application or whatever. So that's really powerful.
Yeah, I was about to say.
So now the last thing I'd like to talk about today, because I just didn't talk about it. I don't think stop me if I've already talked about this, but let's talk about Gauss's law for magnetism.
No, we haven't talked about it.
Okay, this just takes a moment. We actually did talk about it, I just didn't use the words. So if I have a magnetic field, you know, let's take, for example, the magnetic field of a dipole. Can I just get a picture? I don't want to draw one. I don't want to draw this because it's going to look really bad if I do. So let's just use like that. That's good. That doesn't really matter what we use. Let's just take this one. Probably going to copy all of them. That's fine though. Okay, so let's look at these magnetic fields. Okay, and remember what Gauss's law says. Gauss's law says what happens when I integrate a surface integral of the magnetic fields dot product with dA. And remember that flux, we can define something called magnetic flux as being equal to basically just, well, that integral right there, right? This is flux. Surface integral of B dot dA is flux. Or just basically field times area gives you flux, right? Okay, so the question is, what do you get when you evaluate this over a closed surface, okay? So to keep things simple here, what I'll do is I'm going to draw a closed surface in here. Now, the surface that I'm drawing is really not going to be a total surface because it's a ring on the page, so it's really the cross-section of the surface with the page. But imagine that I draw a sphere right here, okay? And that this is the cross-section that it makes with this plane. Because remember, these magnetic fields, they're three-dimensional, okay? So there's also a field line that comes out from the north and goes into the south here, but it goes like out of the page, right? But whatever, we're only looking at a two-dimensional picture, so we'll use a two-dimensional surface. So in evaluating B dot dA, we figured out that really all you need to do is, if you want to get a conceptual understanding of what's going on here, is just count the number of electric field lines that come in and come out. So if a field line goes in, you get positive flux, and if it goes out, you get negative flux, right? So the question is, how many lines actually go in and out of this surface S? Well, I see that there's a line that comes in here and a line that goes out there. The net flux due to that line is 0, right? I see a line that comes in here and it goes out here, so the net flux is 0. Same thing here and here, here and here. Every line that comes in also goes out, right? Does that make sense? So through this surface, what would the flux be?
0.
0.
It'd be 0, right? So that is pretty much what you're always going to get with magnetic fields. This is Gauss's law for magnetism. And the reason why is pretty easy to see if you compare it to Gauss's law for electric fields. For electric fields, what you get when you do the integral of E dot dA is you get the charge enclosed divided by epsilon naught, right? But this is electric charge, and there is no such thing as magnetic charge. So another way to put it, when you describe Gauss's law for magnetism, is that there are no magnetic charges. If there were, if magnetic monopoles existed, they would show up right here as like a Q sub m, magnetic charge or something like that, okay? But they don't. So, you know. Okay, so does anyone have any questions? One thing that's a little bit confusing about this picture, I realize now, is, and maybe some of you are thinking this, what would happen if I chose this point right here? What if I make that surface?
It would have flux.
It would have flux.
Yeah.
Now the reality, though, is that this picture is extremely inaccurate. So just, this picture makes it seem, right, like there's such a thing as a North Pole isolated and a South Pole isolated, right? But this isn't a realistic picture. The other three are, though. So you cannot do that on any of the other three pictures. Because this is the dipole, right? And you're not going to find a place where you see all of the lines going into one location, right? Same thing here. This is like a loop of wire where the wire's coming out and then back into the screen. You can't do that here anymore. Would you all agree? It's really only on this picture. This picture just isn't very accurate, so I guess this was the wrong one to work with. But would you all agree that there's you try as hard as you can, like try a surface like this and try a surface like this and a surface like this and whatever you want. Just try to draw surfaces, and you're going to find that no matter what surface you draw, every line that goes in also comes out at some point, basically. Even if you're really tricky about it. Right? Does that make sense?
Mm-hmm.
Yep.
Okay, so that's Gauss's law for magnetism. It basically says there is no such thing as magnetic monopoles. Now, it doesn't mean that some point in the future we won't find magnetic monopoles. It would be great if we actually could find some way to either produce magnetic monopoles or to kind of fake it, have some kind of like pseudo monopole or something like that. And there's a lot of efforts out there to do that because there could be some nice applications of this if we could figure out a way to isolate magnetic charges. And I guess I'll leave you with one final thought, because this field of looking for magnetic monopoles is really, it's definitely a hotbed of research, in spite of the fact that for 150 plus years the theory tells us they don't exist, right? But that's never stopped physicists from trying. Scientists never stop trying to find new things, even if everybody tells you it's impossible. What would you do if someone told you something was impossible, but you thought that there's a chance? You'd probably try to do it, right? So scientists are always looking for these things. And one really interesting idea that I learned about, which I really like, is adding wormholes into this. So one way that people have thought of monopoles existing, and this has to be like kind of more on a galactic kind of scale, but imagine you have a wormhole. So what's a wormhole? So a wormhole is basically something that is predicted to exist from Einstein's theory of general relativity. Within that theory, they talk about something that's called an Einstein-Rosen bridge, and nowadays we just call them wormholes. Okay, and wormholes obviously show up in all types of science fiction because it's a really fancy way to get between two locations in space that is also motivated by science. So the idea would be that if Earth is over here, okay, and let's say over here we have let's just take a distant star. So let's take like, let's pick something different. Okay, let's just say this is the center of the galaxy. Okay, Now, the distance between the Earth and the center of the galaxy, anyone here really good with astronomy know the answer to that? I think it's like 20,000 light years. Maybe it's 20 million light years. I don't really know. But let's say it's 20,000 light years, okay? The actual distance, okay? So what a wormhole would do, it would make it so that you could travel through that distance in some type of a spacecraft. So here's your spacecraft. In a much smaller amount of time. So normally if it was 20,000 light years and you were in a spaceship traveling near the speed of light, it would take 20,000 years to get there. That's what a light year is. It's the distance the light travels in a year. So if your spaceship was traveling, let's say, much smaller speed, it could still get from the Earth to the center of the galaxy by traveling through this wormhole. Because the whole point of a wormhole is it connects two distance points in space-time. Now, there's a lot of things we don't know about wormholes, like maybe it actually takes just as long to travel through the wormhole as it would to travel in a straight line. We just don't know, but we think that it's a way to circumvent traveling long distances through space. Now, how are wormholes produced? Maybe they occur naturally. Maybe you have to generate a wormhole with a huge amount of energy that's pumped into space. We really don't know yet. This is it's definitely future tech. But that's why it shows up in sci-fi shows, like in, I don't know, Star Trek Deep Space Nine. Does anyone... That's a really old show. Has anyone ever seen that show? Does anyone here watch Star Trek at all? So in this show, there's a space station that's located right outside of a wormhole that connects to it, like a distant galaxy or a distant part of the galaxy or something like that. And anyway, what about you guys have probably seen Interstellar though, right?
Yeah.
Yeah.
Okay, so they go through a wormhole in Interstellar, right? They find there's a wormhole that shows up, like just outside of Jupiter or something like that, and it's really cool the way they did it in the movie because it's like this spherical object, and they kind of like fall into it, and they end up basically in another part of the galaxy near a black hole, and they're looking for a planet that humanity can move to, right? So that's what a wormhole is. It's a pretty cool thing, right? Okay, so suppose that I have a wormhole now. Let's tie this back to what we're talking about. So here's our wormhole. I'm not going to pretend that I have any ability to make an artistic representation of what a wormhole would look like. And then suppose that you have a magnet, okay? But the magnet, basically, the bulk of the magnet is inside the wormhole, and so let's say that's the north end and that's the south end of your magnet right there. Well, now, if you didn't know there was a wormhole here, all you would see would just be the north end of a magnet. And now this would be a monopole, technically. At least from your perspective, right? Because now all of the field lines for this object would be emanating out just like this one right here. Now, even though there are technically magnetic field lines that are going in, it would have the magnetic field of a monopole because the other pieces of this, the place where these wrap back around, would be thousands of light years possibly away from this location. So that's one idea for monopoles, that if you could have a wormhole, you could probably produce a monopole by embedding a magnetic field inside of it, or by embedding a magnet inside of it. And then maybe you could do something with those monopoles. I don't know. But yeah. Okay, so that's where